Welcome to the Building Envelope case study with RETScreen. To demonstrate how to prepare a building envelope study using RETScreen, the rest of this video will walk you through a case study based on a school in Slovakia. In this scenario, a school building and adjoining caretaker flat are connected to a district heating system from which the school purchases heat, and there is no provision to separate the heating loads. As a result, the school has to be fully heated during unoccupied hours and on weekends when not in use. A RETScreen file for this project has been provided with relevant information filled out for most categories on the start page. This can be accessed at the following link. Once we've done this, let's tick the box in the Show Settings checkbox to unveil language, currency, and unit system selection. Using the drop-down list, let's confirm that English has been selected for the language, Slovakia for the currency, as the monetary data of the project will then be reported in Slovak koruna or SKK, and metric units for the unit system in which outputs will be displayed. Note that this analysis will use weather data relevant to an older version of RETScreen 4, as the current RETScreen weather data is slightly different and would give different results. Let's move on to the Energy Model worksheet. Click on the Energy Model tab at the bottom of the screen for the Complete Energy Model sheet hyperlink to access the Energy Model worksheet. In the Fuels and Schedules section, we will enter information about the fuels and schedule considered for the base case and the proposed case facilities. At the outset of an energy efficiency project, we need to determine the types of fuels used, the amounts consumed, and the associated fuel rates or per unit cost for the fuels. Since this case study does not specify the fuel name but provides the fuel characteristics, let's select UserDefined Fuel from the drop-down list for Fuel Type 2. Now, let's go to the Tools worksheet and select UserDefined Fuel. For reference purposes only, let's enter the name of the fuel type, which we will call District Energy. The fuel consumption unit value corresponds to the unit of the fuel type selected and is automatically displayed except for when the fuel type is User-Defined Fuel. Since the fuel rate identified in the case study is given in Slovak koruna per gigajoule units, select Energy Units in order to have the Fuel Consumption Unit drop-down list offer gigajoule as one of the options. The User-Defined Fuel tool is also the place to enter the fuel emissions figures which have been provided by the district energy company in charge of the district heating system. These are 77.8571 kilograms per gigajoule of carbon dioxide, 0.0057 kilograms per gigajoule of methane, and 0.0014 kilograms per gigajoule of nitrous oxide. These values represent the mass of the specific greenhouse gas emitted per unit of energy generated and are used by the model to estimate the greenhouse gas emissions. The completed user-defined fuel data from the Tools worksheet is shown here. Now, let's return to the Energy Model worksheet. The fuel consumption unit and the fuel rate unit are now displayed for fuel type 2. The only remaining entry required in this section is the fuel rate for fuel type 2. Let's enter 585 Slovak koruna per gigajoule, which has been provided as the fuel rate in the initial case study parameters. Operating schedules are used in the calculation of weather-dependent heating and cooling loads, or loads resulting from the building envelope and ventilation characteristics. RETScreen automatically includes a 24/7 schedule. The base case specifies 20 degrees Celsius as the space heating temperature on a 24 hours per day basis. Let's enter 20 as the desired space heating temperature set point for Schedule 1 as well as for Schedule 2, which represents the proposed case facilities. Also, The desired space cooling temperature set point will be set to 20 for Schedule 1 as well as for Schedule 2. The proposed case specifies lowering the set point temperature for heating by 2 degrees Celsius when the school is not occupied on weekends and for 12 hours each weekday. The temperature unoccupied cell under Schedule 2 represents the difference between temperature set points for occupied and unoccupied periods for that schedule. In this context, the setback temperature for space heating will be 2 degrees Celsius lower during unoccupied periods, and the set-up temperature for space cooling will be 2 degrees higher during unoccupied periods. Hence, we will enter a value of 2 degrees Celsius. The occupancy rate daily cell is used to calculate the number of hours per year that are considered as occupied periods for each schedule specified. The model also calculates the occupancy rate in percentage for the entire year. In this particular study, since there is no provision to separate the heating loads between the school and the adjoining caretaker flat, the school has to be fully heated during unoccupied times, such as during weekends and summer months. In other circumstances, we could account for closure during certain periods of the year by modifying the heating degree days and cooling degree day values entered in the climate data area of the START worksheet. We will enter 12 to correspond to 12 hours of heating Monday through Friday, and 0 to correspond to 0 hours on Saturday and Sunday for Schedule 2, as this is what has been provided by the case study. The heating-cooling changeover temperature refers to the outdoor air temperature at which the HVAC system will normally change from heating to cooling and vice versa. The model calculates the length of the heating season and the length of the cooling season based on the heating-cooling changeover temperature and the climate data entered in the START worksheet. For this, let's enter 16 degrees Celsius, which has been provided for this case study. In the Facility Characteristics section, we will enter information for the base case and the proposed case facilities. RETScreen deals with the efficiency measures applied to the heating system, cooling system, building envelope, ventilation, lights, electrical equipment, hot water, pumps, fans, motors, and more. The results displayed for heating, cooling, and electricity depend on the option selection from the drop-down list just below the Show cell. We can also select different energy units in which to display these results. For this study, let's select Fuel Saved and gigajoules as the heating unit. We will ignore the cooling and electricity portions as there is no related data in the case study. The model displays the incremental initial costs associated with each energy efficiency measure as entered in the respective form, as well as the incremental fuel cost savings, O&M savings, and simple payback associated with each energy efficiency measure. Each individual energy efficiency measure can be included or excluded from the final calculations by ticking the Include Measure checkbox to the right of Measure. If the Include Measure checkbox is not ticked, the proposed case is considered to be equal to the base case. The energy performance of a heating system is influenced by a number of factors. The main ones typically include the type of fuel used and the seasonal efficiency of the heating equipment. Let's click on the Heating System hyperlink to open the Heating System form, and enter District Energy as the description of the school's heating system. In our case, the fuel type is Fuel Type 2 for the base case and proposed case, and is automatically populated by the selection made in the Fuels and Schedules section of the Energy Model worksheet. In order for RETScreen to calculate the energy input required by a heating or cooling system, we must specify the equipment's seasonal efficiency. The seasonal efficiency is the ratio of the heating or cooling energy actually delivered divided by the total energy available in the fuel consumed, considered over the entire year. Thus, if on an annual basis a heating system consumes fuel containing 100 gigajoules of energy, but produces only 55 gigajoules of heat, its seasonal efficiency is 55%. Note that because the system may operate at part load, cycle on and off, and otherwise be subject to non-ideal operating conditions, the seasonal efficiency is almost always lower than the steady-state efficiency found in manufacturer's literature. In this particular case, the school is purchasing its heat from a district heating system and not producing anything. Thus, in this context, since the school is only paying for the fuel delivered, the efficiency is 100%. Let's enter 100 as the percent value for seasonal efficiency for both the base case and proposed case. The incremental initial costs and the O&M savings values typically include both equipment and installation costs. In this particular case study, it is the cost associated with heating schedule changes. Let's enter 600,000 as the value for incremental initial costs for the proposed case. Since the incremental O&M savings are not specified in the case study, that item is left blank. Now, let's click on the green checkmark button to copy the values from this form to the energy model worksheet. The energy performance of a building envelope is influenced by a number of factors. For example, these may include design elements such as the physical orientation of the building and the amount of sunlight that penetrates into the interior living or workspaces. Other factors may also include the heat transfer characteristics and the location of the building, as well as envelope components including walls, windows, doors, floors, and the roof. The energy performance of a building may also be influenced by any natural air infiltration through the building envelope. The building envelope schematic shown here provides an overview. RETScreen's building envelope model is used to evaluate the energy use and savings, costs, emission reductions, financial viability, and risk for building envelope energy efficiency measures. The model also considers the impact of one or more operating schedules for the base case and the proposed case building, and it models the cross effects of other energy efficiency measures employed in the facility. In addition, the effective thermal resistance or thermal conductance of a specific building envelope assembly can be calculated using an optional building envelope properties tool. Let's click on the building envelope hyperlink to open the building envelope form. The form allows for up to 5 distinct building envelope descriptions. Since the case study deals with 2 separate buildings, 2 models will be required. Let's go through building envelope 1 in detail. First, let's enter school in the description item for building envelope 1. The building north value corresponds to the angle measured in degrees between the north face of the building and the true north with due north equal to 0. Note that compasses point to magnetic north, and directions based on this measure must be adjusted for the magnetic declination. For example, a magnetic declination of 10 degrees east means that magnetic north is 10 degrees east of true north for that location and time, and that value would be entered as plus 10 degrees in RETScreen. Conversely, with a magnetic declination value of 10 degrees west, the building north value would be entered as negative 10 degrees to reflect that this building's north face is directed 10 degrees west of true north. Let's enter 0 in this cell, as the case study has specified that the north side of all the buildings face due north. Let's tick the base case equals proposed case checkbox to indicate that this is indeed the case for this study. For parts of the building envelope that are identical for both the base case and proposed cases, RETScreen provides a means to copy the data from the base case to the proposed case. Let's also do this for the remaining aspects of the envelope analysis, because we know this to be relevant, and so that the base case cells are automatically transferred to the proposed case cells. The operating schedule for the building under consideration is selected from the drop-down list. As established previously, base case schedule is Schedule 1, and the proposed case schedule is Schedule 2. In this cell, the gross exterior wall area, including windows and doors, in each of the 4 cardinal directions should be entered, and we have the option of selecting either square meters or square feet as the units. By default, walls is the only building envelope element displayed when the building envelope form opens. For this project, let's enter 390 square meters for north and south walls and 200 square meters for east and west walls for the school building in the base case cells for wall area, as this is what has been provided in the case study. The R value is a measure of thermal resistance used in the building industry. It is the ratio of the temperature difference across a material and the heat flow through it. The larger the value, the greater the resistance to heat flow across the material. R value is the reciprocal of U value, which is the overall heat transfer coefficient and describes how well a material conducts heat. In Europe, it is customary to use U values instead of R values. RETScreen allows the user to enter either R values or U values by selecting the corresponding units. R value units are given in square feet per degrees Fahrenheit per BTU hours or meter squared per degrees Celsius per watt, while those for U value are the inverse, given as BTU hours per square foot per degrees Fahrenheit or watts per meter squared per degrees Celsius. RETScreen uses effective thermal resistance or thermal conductance values in its building envelope model. Effective or in-service R values reflect the total resistance provided by all components in a building assembly. Nominal R values are the rated values of a material and do not account for thermal bridging in the building envelope, such as steel or wood studs and exposed floor slabs. The effective R value is typically lower than the nominal R value. The Building Envelope Properties feature in the Tools section estimates the effective R value or U value for walls above and below grade, floor and roof based on cavity, frame, and additional envelope penetrations. Let's enter the information shown here for the presumed layer types and the corresponding thickness for each layer to obtain an R value for this project. In this example, factors that would reduce the nominal R value, such as framing and envelope penetrations, were not specified. Therefore, the nominal and effective R value are equal at 0.745. Let's return to the envelope section in the energy model and enter 0.745 R value in meters squared per degree Celsius per watt for each wall for the school. Note that if we leave an R value cell blank, the model will not consider this wall in the calculations. In this particular study, the incremental initial cost cell is left blank as there are no incremental initial costs or credits for the proposed case. As the case study supplies information about windows, tick the checkbox next to Windows to indicate that a detailed Windows analysis is to be conducted. The window area entry method depends on the unit selected. If square meters or square feet is selected, then the value entered will be the actual window area including the window frame. If percentage is selected, then the value entered would be the window area as a percentage of the gross exterior wall area entered above. The model will then automatically calculate the net wall area based on the gross wall area to account for the percentage of window area. As shown here, let's enter 15 as the percentage of school wall area occupied by windows for each of the 4 cardinal directions. Similar to the walls building envelope element, the R value or U value can be entered by selecting the corresponding unit. The effective value accounts for thermal bridging in the window frame and is typically lower than the nominal R value and vice versa for the U value. RETScreen provides a detailed window properties tool as a companion tool to determine the effective window properties and individual window costs. This tool is useful when windows of different sizes and/or different properties are installed on the same face of the building. Frame effects can also be accounted for to adjust U values and solar heat gain coefficients from rated values when windows differ from the rated size. The Window Properties tool is accessed by clicking on the Tools tab and Window Properties and then clicking on the blue hyperlink or on the Window Worksheet tab that appears at the bottom when this tool is selected. Columns assessing orientation, type, width, height, cost, number, area, center glazing, rated window, and adjustments are provided and can be populated via the RETScreen product database. For this study, the R value for the windows has already been identified as 0.36 regardless of the orientation. Thus, we will enter 0.36 in all 4 cells. The solar heat gain coefficient, or SHGC, is a dimensionless quantity representing the fraction of the solar energy incident on the window that ends up as heat inside the building. The effective value takes into account the opaqueness of the window frame. For the purpose of this study, we will enter 0.65 for each orientation for the school building. A shading factor represents the fraction of a window surface area that is shaded from direct sunlight by an obstruction such as an adjacent building, vegetation, or a shading device like an awning. The shading factor is the reduction in solar gains due to shading and is not associated with the shading coefficient of the window. There is no solar shading of the windows in this particular study. Therefore, this section does not need to be included in the analysis. Since the case study contains data related to doors, let's click on the checkbox to conduct a detailed doors analysis. The model will then automatically calculate the net wall area based on the gross wall area to account for the percentage of door area. Let's enter the school door area data, which is 2% of gross wall area for north and south walls and 4% of gross wall area for east and west walls. As was the case with windows, for this case study, the R value for the doors has been identified as 0.36 regardless of the orientation. Thus, we will enter an R value of 0.36 in all 4 cells. Since the case study contains roof data, click on the checkbox to conduct a detailed roof analysis. The roof area of relevance here is the one corresponding to the plane through which primary heat loss occurs. For flat roofs and insulated vaulted roofs, the value to be entered is the area of the roof itself. For attic-style roofs, the value to be entered is the area of the insulated horizontal plane. For the purpose of this study, we will enter 2100 as the school roof area and ensure that the unit selected is meters squared. For our roof R value, a value of 2 has been provided. Let's input this into the corresponding cell. Since the case study contains floor data, let's tick on the checkbox to conduct a detailed floor analysis. The floor area of relevance here is the total area of the exposed floors corresponding to the plane through which primary heat loss occurs. Exposed floors are those that are directly connected to the exterior ambient temperatures. Floor exposed to unheated spaces would be included. For the purpose of this study, we will enter 2100 as the school floor area and ensure that the unit selected is meters squared. For the floor R value, we will input a value of 0.5 as designated in the case study. The building envelope properties tool could also have been used to estimate the effective R value or U value of the roof or floor. However, these values were already provided, so we will skip this step. The total area of all walls below grade can be entered in these cells here. Similar to the previous sections, the building envelope properties tool can be used to estimate the effective R value or U value of the wall or floor below grade. The walls below grade refers to the total area of all walls below grade, and the floor below grade refers to the foundation slab located under the ground. However, as this study does not include wall or floor below grade data, these sections do not need to be included in the analysis. The second part of the building envelope analysis for the school will cover the natural air infiltration, which is covered in the second part of the form, accessed by clicking on the next hyperlink at the bottom of the form. To determine the annual energy needs to heat or cool this air, the average volume rate of air movement must be determined. The natural air infiltration is known, such as through a blower door test. The user-defined option is selected from the method drop-down list, and this value is entered directly in the natural air infiltration cell below. If this value is not known, it can be estimated using other methods. The calculated method allows the user to describe the leakiness of the walls, windows, and doors by selecting whether these envelope elements are leaky, medium, or tight. This is a subjective selection and is typically based on building type and the age of the building, windows, and walls. The model then calculates the overall average natural air infiltration. The air change rate method allows the user to enter the average air changes per hour associated with the natural air infiltration. This method is often used for residential applications since most single-family homes have a similar volume to envelope surface area ratio, and therefore the air change rate can be used to compare different buildings. With this method, the value to be entered for the volume item represents the total volume of heated or cooled space. Also with this method, the value to be entered for the air change rate item represents the number of air changes per hour. One air change per hour is equivalent to introducing the volume of fresh air into the building every hour. Typical values range from 0.2 to 2 air changes per hour. The model then calculates the overall average natural air infiltration. The crack method allows the user to enter the equivalent crack area. The equivalent crack area represents the equivalent size of a hole in the wall through which infiltration occurs. The model then calculates the overall average natural air infiltration. The leakage method allows the user to enter the average leakage rate per area of building envelope. This method is often used for commercial applications since in these types of buildings, infiltration occurs mostly through the envelope and not through cracks around windows and doors. Under normal operation, air leaks through the building envelope are driven by wind or stack effect. Thus, the hour-by-hour air leakage changes according to wind speed and temperature. Typical air leakage rates range from 0.05 to 1 liters per second per meter squared of building envelope area for most buildings and climates.
In our case, let's select the air change rate method and enter 11,500 meters squared as the school volume and 1.5 as the air change rate value, which has been provided in the case study. The average natural air infiltration represents the amount of fresh air that has to be heated or cooled. In this study, RETScreen then calculates average natural air infiltration at 4,791.7 liters per second for the school. The total incremental initial costs or credits for the proposed case is multiplied by the number of building envelope units and copied to the energy model worksheet when the green paste button is clicked. The total incremental operations and maintenance savings or costs for the proposed case is multiplied by the number of building envelope units and copied to the energy model worksheet when the green button is clicked. If the savings for the proposed case are equal to those that would have been spent for the base case, this item is left blank. As there are no incremental O&M savings specified in this study, we will leave this item blank. The number of similar building envelope units is the number of separate buildings in a facility connected to the same heating and cooling plant under consideration. As the school and the caretaker's apartment are adjoined and there is no provision to separate the heating loads, we will enter 1 as the value for both the base case and the proposed case. The system selection value refers to the type of system under consideration. If the building is both heated and cooled over the course of the year, then the heating and cooling option would be selected from the drop-down list. In this study, we will select heating as the type of system since the district heating system only handles the heating load. The heating systems are specified in the heating system form. In this study, only one heating system is specified, district energy. Thus, let's select Heating System 1 from the drop-down list for both the base case and the proposed case. The description of the heating system selected is displayed for reference purposes only. Since there are 2 distinct buildings, details for the caretaker's apartment are entered in Building Envelope 2. Here, let's input the following data that have been provided in the case study. For For building north, a value of 0. For base case and proposed case schedule, schedule 1. For the wall area, 30 meters squared. And for the R value, 0.745. For the windows, we will input area percentages of 15 for north, 10 for east, 20 for south, and 15 for west, and an R value of 0.36, and a solar heat gain coefficient of 0.65. The apartment only has doors on the east and west with percentage areas of 10 and R values of 0.36. Finally, the roof has an area of 100 meters cubed and an R value of 2, and the floor has an area of 100 meters cubed and an R value of 3. Let's enter the natural air infiltration component data for the apartment. For method, let's select air change rate with a corresponding volume of 300 meters cubed and an air change rate of 1.5 AC per H, which gives us a natural air infiltration of 125 liters per second. The number of building envelope units will be 1, the system selection will be heating, and heating system will be heating system 1. Let's click on the green Paste button to copy the relevant values from the building envelope form to the Energy Model worksheet. The completed facility characteristics section is depicted in the figure shown here. This section summarizes key information for the base case and proposed case facilities, including detailed information for each fuel type used, as well as fuel consumption and annual energy use information for heating, cooling, and electricity. This section also provides a tool to allow the user to benchmark their project for various energy and reference units. For the base case and proposed case facilities, the model summarizes the fuel rate for each fuel type, the annual fuel consumption for each fuel type, and the annual fuel cost for each fuel type. The model also calculates the fuel cost savings as the difference between the base case and the proposed case. The project verification option allows the user to make sure there were no major errors made while modeling the base case facility. It can also be used after the project has been implemented to help verify if the proposed case project has been implemented properly or if the energy performance of the facility degrades over time. This can be done by comparing the fuel consumption calculated by the model with the historical fuel consumption found on electricity or fuel bills. For existing facilities, the user can enter the fuel consumption for the existing building in the fuel consumption historical cell and verify if the fuel consumption base case is similar to the one found on electricity or fuel bills using the fuel consumption variance. If these values are not reasonably close, then the user can review the values entered to help determine any major input errors. Since we do not have existing fuel consumption data for this project, we will not verify this project. For the base case and proposed case facilities, the model summarizes the fuel consumption or energy use and fuel saved for heating, cooling, and electricity. To toggle between fuel consumption and energy statistics, we can click in the yellow cell and select the desired option from the drop-down list. The benchmark option allows the user to display the units for fuel consumption and annual energy use in different units. For example, benchmark data typically available in the literature for energy use of a house might be found in kilowatt hours per meter squared units. For this project, we will not be benchmarking against similar buildings. Normally at this stage in a RETScreen analysis, we might conduct an emissions analysis to analyze the greenhouse gas emission reductions associated with the implementation of the project. However, for this project, we will skip this step and continue on to the financial analysis. The financial analysis section, with its financial parameter input items and its calculated financial viability output items, allows the project decision maker to consider various financial parameters with relative ease. The items entered here are used to calculate the financial viability indicators. The inflation rate is the projected annual average rate of inflation over the life of the project. Let's enter 2% as this has been specified in the case study details. The project life is the duration over which the financial viability of the project is evaluated. Depending on circumstances, it can correspond to the life expectancy of the energy-related equipment, the term of the debt, or the duration of a power purchase agreement. Let's enter 25 years, as this is what has been specified in the case study details. The debt ratio is the ratio of debt over the sum of the debt and the equity of a project. The debt ratio reflects the financial leverage created for a project. The higher the debt ratio, the larger the financial leverage. The model uses the debt ratio to calculate the equity investment that is required to finance the project. Let's enter 50% as specified in the case study details. The debt interest rate is the annual rate of interest paid to the debt holder at the end of each year of the term of the debt. The model uses the debt interest rate to calculate the debt payments. At a minimum, the debt interest rate will correspond to the yield of government bonds with the same term as the debt term. A premium is normally added to this rate to reflect the perceived risk of the project. Let's enter 5% as specified in the case study details. The debt term is the number of years over which the debt is repaid and is either equal to or shorter than the project life. Generally, the longer the term, the more the financial viability of an energy project improves. The model uses the debt term in the calculation of the debt repayments and the yearly cash flows. For the debt term, let's enter 10 years as specified in the case study details. The total initial costs represent the total incremental investment that must be made to bring the proposed case project online before it begins to generate savings or income. These costs are inputs in the calculation of the simple payback and the project equity and debt. The energy efficiency measures item represents the incremental initial costs, or the sum of the design, purchase, and installation costs of all the elements of the energy system related to energy efficiency measures for the project, less any credits for not having to design, purchase, or install base case equipment and materials. For this, we know that 600,000 Slovak koruna has already been factored in previously, and we can see that it has been carried over to this section. The other cell captures all the other incremental costs not considered in any of the other initial cost categories that are required to bring a project to the operational stage. As there is no other cost specified in this study, we will leave this item blank. The incentives and grants item captures all contributions, grants, subsidies, etc. paid for the initial costs of the project. As there is no incentive specified in this study, we will leave this item blank. The total annual costs are calculated by the model and represent the yearly cost incurred to operate, maintain, and finance the project. The model displays the incremental O&M costs or savings of all the elements of the energy system, including the total fuel cost for the proposed case, which is the annual value of fuel cost for the proposed case escalated at the inflation rate, and the debt repayments, which are the sum of the principal and interest paid yearly to service the debt and other costs or savings not considered in any of the other annual cost categories. The total annual savings and income represents the annual savings or income realized due to the implementation of the proposed case. The model displays the total fuel cost for the base case, which is escalated at the inflation rate. The other item captures all the other savings or income not considered in any of the other annual savings or income categories. We have not been informed of any relevant value for this project, so we will leave this item blank. All the items covered so far in the financial analysis section are used to calculate the various financial indicators and to generate a cumulative cash flows graph for the project. The pre-tax internal rate of return on equity, or pre-tax IRR on equity, represents the true interest yield provided by the project equity over its life before income tax and is calculated using the pre-tax yearly cash flows and the project life. It is also referred to as the return on equity or return on investment or the time-adjusted rate of return. The most obvious advantage of using the internal rate of return indicator to evaluate a project is that the outcome does not depend on a discount rate that is specific to a given organization. Instead, the IRR obtained is specific to the project and applies to all investors in the project.
For this project, RETScreen calculates a pre-tax IRR on equity of 50.9%. The pre-tax IRR on assets represents the true interest yield provided by the project assets over its life before income tax. It is calculated using the pre-tax yearly cash flows in the project life. For this project, RETScreen calculates a pre-tax IRR on assets of 27%. Simple payback represents the length of time that it takes for a proposed project to recoup its own initial costs out of the income or savings it generates. The basic premise of the simple payback method is that the more quickly the cost of an investment can be recovered, the more desirable the investment. The model uses the total initial costs, the total annual costs, and the total annual savings and income to calculate the simple payback method. RETScreen calculates a simple payback of 3.3 years for this project. The equity payback represents the length of time that it takes for the owner of a project to recoup its own initial investment out of the project cash flows generated and considers project cash flows from its inception, as well as the leverage of the project, which makes it a better time indicator of the project merits in the simple payback. The model uses the year number and the cumulative after-tax cash flows in order to calculate this value. For the equity payback, RETScreen calculates a value of 2 years for this project.
The financial analysis section is accompanied by a cumulative cash flows graph. This represents the estimated sum of cash that will be paid or received each year during the entire life of the project.
The cumulative cash flows graph corresponding to this study shows that cash flows are positive at about 2 years.
Even though this case study did not propose building envelope related improvements, documenting the performance of the building envelope was necessary to estimate energy use reduction from the heating schedule changes. Ultimately, the success of any facility-wide energy management program requires an accurate assessment of the performance of the building envelope in order to contribute to the effectiveness of energy efficiency measures.